So we're going to do a little review of some stoichiometry calculations, and so first off I would start off by writing down this balanced equation. So we've got potassium phosphate, a little AQ next to it, doesn't really affect the balanced equation, but I'm going to write it down just to have it there. It's K3PO4 plus iron 3 nitrate, so that's FeNO32, and that yields potassium nitrate, there's a 3 in front of it, plus iron 3 phosphate FePO4. So this is actually precipitation reactions. You'll notice that a double replacement reaction. Notice the AQs on the reactants and the AQ on one of the products, and then a solid over here. So we'll get to that later on, why that's significant. So here's our question. How many grams of potassium nitrate are formed by 18.5 grams of potassium phosphate reacting with excess iron 3 nitrate? So again, the wording that something's reacting with an excess of something. Notice the iron 3 nitrate is one of our reactants. That just means if there's plenty of it, we don't have to worry about that as a part of our calculation. If we're doing a limiting reactant problem, we would be given an amount for that and would have to do some calculations with that, but we're not there yet. Okay, so 18.5 grams of potassium phosphate, that is our given information. And again, it's important to recognize which thing potassium phosphate is. So looking at the formulas in the balanced equation, this thing is potassium phosphate. So that's what we've been given an amount of. The thing that we're looking for, it says how many grams, I'm going to underline that, how many grams of potassium nitrate are formed. So notice by that wording we can tell we're looking for something to be a product, and so here's the potassium nitrate. Okay, so again, my given is 18.5 grams. And I want to get in the habit of writing down the formula of my given substance from the balanced equation. So you would not be including coefficients. That's not a part of the identity of the substance. K3PO4 is the formula for potassium phosphate. So that's my given. So I want grams of potassium nitrate. So remember that since we're talking about a balanced equation, we're talking about a reaction, we need to use the balanced equation to answer the question and to look at the recipe of how many of these react to form how many of these. And these substances in the balanced equation are in terms of moles. So that is very important for us to understand because, again, even though this problem does not mention moles, I know that I need to use the balanced equation as my recipe. In order to use the balanced equation, I need to have moles. So we know at some point we're going to use the coefficients from the balanced equation. And if I don't have moles to begin with, I can't use the coefficients from the balanced equation until I do have moles. So that's the theory behind the 3 steps that I've given you. So step 1 is if I don't have moles yet, find moles. So 18.5 grams of potassium phosphate, I want to convert that to moles. The reason I want to write down that this is potassium phosphate is that if I don't know the identity of the substance, then I don't know which molar mass to use. So I want to use the molar mass of potassium phosphate. So potassium has a mass of 39.1, and there's 3 of them, plus phosphorus is 31.0, plus oxygen is 16.0 times 4, so that's 64, and that gives me 212.3. So this is moles of potassium phosphate. So for every 1 mole of potassium phosphate, the molar mass is 212.3 grams. So this is from adding up the masses from potassium phosphate. And again, if you're having trouble, I know this isn't the clearest camera shot, make sure you're listening to the numbers that I'm saying. So 18.5 grams divided by, so this is the molar mass of potassium phosphate. So it's 3 Ks, 1 P, 4 Os based on the formula that I see up here in the balanced equation. So I have 18.5 divided by 212.3, and that is 0.0871, and that is now moles of K3PO4. So it's very important that you're paying attention to what substance you have and what units you have. So this is, notice, again, if my original number had 3 significant figures, I am required to at least write down that number of digits. So the leading zeros don't count. So this is 1, 2, 3. Leave the number in your calculator though. See, I'm going to leave it on there. I'm not going to erase it. So that way I don't want to introduce any rounding errors until the end. A lot of you just keep chopping off numbers and then you put them back on. You can't do that. That's why your numbers come out so much different than mine. Okay, so the reason we found moles, notice this is still the same substance. It's still K3PO4, my initial substance that I started with. So what I need to do next is then, well, now I want to relate this substance to the substance of interest. which was potassium phosphate, potassium nitrate, because again, we set out to find moles so that we could use the balanced equation, because that gives us the recipe of how many moles of this react to form how many moles of this. Okay, so second step is to use the coefficients from the balanced equation. So as always, the unit I want goes on the top. So again, the overall problem, I don't want moles, but the substance I'm interested in finding out about is potassium nitrate. So in this step, I'm going to find the coefficient of potassium nitrate. So KNO3, that's potassium nitrate. That coefficient is 3. So I'm going to put that on the top. That's the coefficient of the thing I want for step 2. It goes right there on the top of my conversion factor. And I want moles of K3PO4 to go away. I don't want that type of mole anymore. So I'm using this relationship from the balanced equation to give me the type of moles that I want, which is potassium nitrate. So I need to find the coefficient of K3PO4, and that, again, if I scroll over, is this, which is 1. All right, so 1 mole of K3PO4 on the bottom. So the moles of what I no longer want are going to cancel out. So that's why we always position what I want on the top. That's going to be the unit that I end up with. The thing that I want to go away is on the bottom. So I had moles of K3PO4. That's why I put moles of K3PO4. So this ratio comes from the balanced equation. So now I'm using my recipe. So every 1 mole of this K3PO4 makes 3 moles of this. So that then I multiply the number, which is still on my calculator, times 3 divided by 1. So that gives me 0.261, and that is moles of, notice I have it labeled, KNO3. So when you do step 2 using the balanced equation, again, if that was in terms of moles, this ratio is in terms of moles, I end up with moles of potassium nitrate, KNO3. Okay, so this is now moles of potassium nitrate. Third step is find whatever the requested unit is. So in this problem, I was asked for grams of potassium nitrate. So that's what I'm going to find. So how do I get from moles to grams? Well, we know that we are going to start back over here. 0.261, so that's the moles potassium nitrate. And again, I need to use the molar mass. So again, molar mass, I don't care that there's a 3 in front of potassium nitrate when I'm finding the molar mass. The formula for potassium nitrate is KNO3. So the mass of K is 39.1. The mass of nitrogen is 14.0. The mass of oxygen is 16.0 times 3 gives me a 48. And so we add all that up, and that is 101.1 grams per 1 mole. So this is the molar mass. Molar mass is always per 1 mole. So I'm multiplying moles of my wanted substance by its molar mass. And that gives me 26.3871. So again, my original number had 3 significant figures. So since this was all just multiplication and converting units, that would be 26.4 grams. And that is of potassium nitrate. So that's how much potassium nitrate in grams would be formed by reacting that amount of potassium phosphate. Now, another way that we might be given one of these stoichiometry problems is, well, again, I pointed out at the beginning of this, these are solutions. If you remember when we did our reactions involving double replacement, we saw that, solution means that it is, these solutes are dissolved in water. And so remember that the molarity equation, if I have a solution with a certain concentration, I would need to use the molarity equation to help me unlock moles of solute. And so it's moles of solute per liter of solution. So that's the formula for molarity. So let's say that I want to know how many grams of iron phosphate would be formed. So you can just write this out. How many grams of iron phosphate would be formed by reacting 500 milliliters of, let's see here, so we're going to react 500 milliliters of, let's do 0.500 molar K3PO4. And I want to find the mass of iron iron phosphate. So this is more the way a problem like this would probably shake out, because again, we would be measuring out these solutions. We have to measure out some volume of them, right, because they're in liquid form. So there's the text of the problem there. So we have, we're reacting 500 milliliters of 0.500 molar K3PO4. So the fact that I wrote this formula after the capital M tells me that this is the identity of the solute. So when I look at the molarity equation, what I need is, well, I have a molarity, right? I have this 0.50 molar. I want to find moles as my initial step for this problem, and because I'm given a solution volume, so my volume, notice, is 500 milliliters, I would use that in liter form, along with my molarity. I'm going to solve for moles of solute. So if I'm given a problem that involves a solution, I need to use the appropriate tools to find the moles of solute. So I'm going to rearrange this equation, and essentially it's going to be the molarity times the volume. The volume has to be in liters. So again, it's going to be, this molarity is 0.500, and that is moles per liter, times 500 milliliters. Again, there's 1,000 milliliters per liter, so that would be converted to 0.500 liters, and that gives me 0.5 times 0.5 is 0.250, and that's moles of solute. Okay, now what is my solute? Well, again, this says it right here. It's K3PO4. K3PO4. Now this is getting messy because I'm getting to the bottom of my paper. Okay, so there you go. Okay, so now then, I have moles. So step one of every stoichiometry problem is find moles. Second step is, well, to go from moles of the thing I'm given to the moles of the thing I'm interested in. So I'm interested in, for this problem, just to review, I was asked about the mass of iron phosphate. So I again go through my 0.250 moles K3PO4. Scroll that down a little bit. And I want to put from the balanced equation. The reason I found moles is so I could use that relationship. So I'm interested in iron phosphate. Let's see, scroll up. So the formula for iron phosphate, notice there's a coefficient of 1. So I have 1 mole of FePO4 is formed for every, well, notice K3PO4 was our reactant given information, so the coefficient of that is 1. So it's a 1-to-1 ratio. So this actually isn't going to change my number at all, but it's important that we show that we have taken into consideration that it's a 1-to-1 relationship. So that then is, meaning we're going to have 0.250 moles of, well, now it's this type of mole, so it's FePO4. And then lastly, so now we're just at the same spot where we were in our last problem. So now I've got the moles of the thing I'm interested in. I was not asked for moles, I was asked for mass, because this is a solid, I'll be able to filter it out and measure it. And so I will find the molar mass of iron phosphate. So iron is 55.8, phosphorus is 31.0, oxygen is 16.0 times 4, that would be 64. So this gives me 150.8 grams per mole. So I'm going to multiply that by the 0.250, and I get 37.7 grams of iron phosphate that will be formed by reacting 0.5 molar, 500 milliliters of 0.5 molar potassium phosphate. And again, we're assuming in this problem that we had plenty of the other reactant since we were just given the amount of 1. So there's 2 examples of stoichiometry problems. Again, same 3 steps. Find moles if you're not given them. Use the moles of one substance to find moles of another through the balanced equation as the recipe. We're going to use coefficients from both of the substances. The substance we want, its coefficient over the substance we no longer want. After that second step, we now have moles of the new thing that we're interested in. And lastly, we find whatever they're asking us for. In these 2 problems, we were asked to find grams of that substance, but you could also be asked to go back and find a concentration of solution or a volume of solution needed for the reaction. And again, that would be just working out algebra involving molarity. So same 3 steps every time. Find moles so that we can use the balanced equation coefficients. It's always the moles of the thing I want over the moles of the thing that was is given. After that step, we have moles of the substance we're interested in, and then we solve in step 3 for the units that were requested.